Hello, everyone. Okay, this will be our last lecture of the semester. There's no lab tomorrow, and I will be sending out the next unit exam sometime tomorrow, and I'll notify you of the due date and time of that. Okay, so that'll cover chapters 8, 9, 10, 11, and 14. All right, so I'm going to go ahead and get started with chapter 11. This is reactions of alcohols. Okay, we'll start out by looking at oxidation. Okay, primary alcohols, such as ethanol, can be oxidized, and we're using chromic acid, okay, which is formed from a dichromate salt and sulfuric acid. Okay, what is the product? So get out some writing paper and pen or pencil to write with. Okay, write down the product. Okay, this is a strong oxidizer. This will take it all the way to the carboxylic acid. Okay, some other methods of oxidizing which stop at the aldehyde stage include PCC, or what's called the Swern oxidation. Swern oxidation is dimethyl sulfoxide and oxalyl chloride. Both of these will allow us to stop at the aldehyde. Okay, there are some other methods as well. Okay, such as sodium hypochlorite. Sodium hypochlorite generally goes all the way to the carboxylic acid. Sodium hypochlorite is bleach, of course. And then there's also the DMP reagent. Okay, that uses a high valent iodine. Okay, the DMP so that uses this reagent, and that also allows us to stop at the aldehyde stage. All right, if we have a secondary alcohol, such as cyclohexanol, and we employ any of these methods, okay, that could be chromic acid or sodium hypochlorite or swern or DMP or PCC. Okay, what's the product we get? Okay, so a secondary alcohol will result in a ketone. Okay. All right, what if we have a tertiary alcohol? Okay, then what? Okay, then it's no reaction. With the primary and secondary alcohols, you break a carbon-hydrogen bond. In this case, there's no CH bond. And if we have something like this, okay, that's too many bonds to carbon, so that can't exist. That's 5 bonds to carbon. Okay, this was covered in an earlier chapter. But what is the product if we have cyclohexanol and we react it with potassium metal? What do we get? This is an oxidation reduction reaction. Hydrogen is reduced, and we get 1/2 H2 gas. And we get the potassium salt. Okay, whereas this is a weak nucleophile and would only undergo reactions as a nucleophile in under SN1 conditions, the alkoxide is now a strong nucleophile. So let me rewrite this over here. If we react this with 1-iodopropane, what's the mechanism in the product? Okay, strong nucleophile, primary halide. All right, this would be an SN2. and our product would be propoxy cyclohexane, or you could say cyclohexyl propyl ether. Okay, next we'll look at tosylate esters. Okay, because OH minus is a poor leaving group, we did a couple of labs where we first converted this to water as a leaving group. Okay, for example, we used terbutyl alcohol and reacted it with HCl. Okay, and now we have water as our leaving group. Okay, this is an SN1, so water leaves. We get this tubutyl cation, and chloride comes in, and we get our tubutyl chloride. Okay, so another way of transforming the poor leaving group OH into a better leaving group is to convert the alcohol to a tosylate ester. Okay, so what we do is we react the alcohol with tosyl chloride in pyridine, okay, TSCl. It's like this. It's TSCl. Pyridine acts as a solvent at the base. It neutralizes the HCl. Okay, now we've got a very good leaving group. The tosylate ester can now serve as a substrate for SN2 or E2 reactions. Okay, and just like with a halide leaving group, okay, let me give you an example here. Okay, say we have something like this. Okay, and we do a substitution, let's say something like CH3S minus. This will come in from the back, and we'll have complete inversion. That will push the hydrogen forward, and SCH3 will come in, will be behind. Okay, there's a whole variety of different compounds that we can make using a tosylate ester. For example, if we used hydroxide as our nucleophile, one useful application of this would be to produce an alcohol with the opposite configuration. So we could make a nitrile if we use Cn-. We could form an ether if we used an alkoxide. We could also convert a tosylate into an alkane. If we use lithium aluminum hydride, that will replace the tosylate group with a hydrogen. Okay, so this is one way to convert an alcohol into alkane. Another way to convert an alcohol into an alkane would be to do a dehydration first. Okay, sulfuric acid and heat, okay, which would give us the alkene. And then we could do catalytic hydrogenation, okay, where we add hydrogen to each side of the alkene. Okay, next we'll look at converting alcohols to alkyl halides. Okay, we did 2 reactions in which we did that in lab this semester. We made 1-bromobutane and 2-butyl chloride, both using strong acids. Okay, there are a lot of limitations to using HCl and HBr. With tertiary and secondary alcohols, we can get a product using the SN1 mechanism. We were able to convert 1-butanol into 1-bromobutane with HBr, which we generated, but HCl doesn't work so well with primary alcohols. Okay, this brings us to something called the Lucas test. This uses zinc chloride and HCl. Okay, this gives us an alkyl chloride. Okay, the alkyl chloride will either form a precipitate or it will turn the solution cloudy. Okay, this is under SN1 conditions. Okay, we have a polar solvent, and we've got a strong acid, so it's SN1 conditions. And so a primary alcohol will react either very slowly or not at all. Tertiary alcohol will react very quickly since it's an SN1. And secondary alcohol usually between 5 minutes and an hour. So we can do a quick test to determine classification. Okay, hydrogen halides. As I mentioned, we get poor yields with alkyl chlorides and primary alcohols and even secondary alcohols. There's also the possibility of elimination, forming an alkene. And we can also have carbocation rearrangement. Okay, so, excuse me. So some alternative ways of making alkyl halides from alcohols. One is to use phosphorus trihalides. Okay, like we use PCl3, you get the corresponding chloride. If we use PBr3, okay, we get the corresponding bromide. And usually for iodides, they'll use elemental phosphorus and elemental iodine. Okay, because Pi3 doesn't last very long on storage. Okay, we can also use a reagent called thionyl chloride SOCl2. Okay, these methods, the phosphorus trihalide, the thionyl chloride, typically give very good yields. And in the case of thionyl chloride, the two byproducts are gases, so that keeps the reaction from going backwards. Okay, the mechanism for reaction with PBr3 . Okay, the alcohol attacks the phosphorus. Okay, and it turns out that this is now an excellent leaving group. So what happens next is bromide will come in. It'll attack the carbon carrying the oxygen and kick this out. And we get our alkyl bromide. Okay, we can also dehydrate alcohols to form alkenes. We saw that in earlier chapters. Okay, this is an E1 elimination.
Can you actually leave that up for just a second more, please? Thank you, sorry.
Okay, this is industrial bimolecular dehydration. It takes place about 140 degrees Celsius. Okay, if we carry this out at 180 degrees, we get ethylene. So in the presence of sulfuric acid, okay, we protonate the alcohol. Then another alcohol comes along. This is primary, so this is going to be SN2. This will attack carbon number 1, kick out water. And then water comes along and moves this hydrogen. and we get ethyl ether. Okay, this is not generally done in the laboratory. This is more of an industrial process. And this only works for symmetric ethers. Okay, a couple of reactions that are unique to diols. This one is a pinnacle rearrangement. Okay, pinnacle is a common name for 2,3-dimethyl butane 2,3-diol. Pinnacle. Write that over here. Okay, so one of these alcohol groups removes a proton from sulfuric acid. Okay, because of hydrogen bonding taking place here, the other alcohol doesn't get protonated. Let's start with this one. Okay, next water leaves. Okay, which gives us a tertiary carbocation. Right, then we have a methyl migration that takes place. Okay, well, this is a tertiary carbocation, and you think, well, that's pretty stable, it's not going to rearrange. This, this carbocation is now stabilized by resonance. Okay, and then what happens next is water back, removes this hydrogen, and we actually get a ketone. A methyl terbutyl ketone, commonly called pennacolone. Okay, the other unique reaction of a diol is the periodic acid cleavage. Okay, so if we have a bisanol or 1,2-diol, and we react this with periodic acid, HiO4, okay, we'll cleave this carbon-carbon bond, and there's a hydrogen here. Okay, so this part becomes an aldehyde, and then this part would be a ketone. Okay, then lastly, in this chapter, we introduce various types of esters. Okay, we're familiar with the carboxylate esters. Okay, which combine carboxylic acid and an alcohol. Okay, but then we also have, we saw the tosylate esters, ROTS. You can have sulfate esters. So this is sulfuric acid. And if we replace these H's with alkyl groups, okay, this is dimethyl sulfate. Okay, and then you can also have nitrate and phosphate esters. This would be trimethyl phosphate. Nitrate esters are usually explosive, okay, such as nitroglycerin. This is nitroglycerin. Okay, and then chapter 14 is a fairly short chapter. Okay, we already talked about the Williamson synthesis where we use an alkoxide and an alkyl halide or tosylate. And back in our chapter on alkenes, we also saw that we could form an epoxide with MCPBA or MMPP. Okay, so let's look at some ether nomenclature. Okay, so draw 3,4-dimethoxy phenol. 3,4-dimethoxy phenol. Okay, in terms of priorities, ethers are one of the lowest priority groups there are. Okay, so here's phenol, and the OH is automatically on carbon number 1. Okay, so a methoxy is an OCH3. Right, name this compound. There's two correct ways of naming this by the IUPAC. Right, one way is to call the parent compound oxirane. So ethylene oxide is called oxirane in the IUPAC. Okay, if that's a parent compound, oxygen is position number 1. And so this would be 2,3-diethyl oxirane. Okay, the other end would be cis. Okay, the other way you could name this, okay, is to call the parent compound 1, 2, 3, 4, 5, 6. That's hexane. And for an epoxy group as a substituent, you actually need 2 numbers. So this is 3,4 epoxy hexane, and it's also cis. All right, so a 3-member ring is called oxirane. A 4-member ring is called oxetane.
Wait, Dr. Trump,
Yeah.
is it possible for me to call this hexane epoxide? I mean hexane oxide? No.
Yeah, it's that would be a common name. So it would be cis-3-hexene oxide. Yeah, that would be a common name. Okay, but these are the IUPAC names. Okay, and then the last thing we'll look at is ring opening of epoxides. Okay, if we have an unsymmetric epoxide such as this, okay, with a strong nucleophile, okay, such as a Grignard, okay, Grignard will attack the less substituted side. Or if we have other strong nucleophiles, would be things like methoxide or something like that. Okay, so this would attack the less substituted side. Okay, so I added the methyl here. And then when we protonate that, that would give us 2-butanol. Okay, if we do this under acidic conditions, if we have, say, methanol and acid catalyst, methanol will attack the more substituted side. Okay, so that's pretty much it. So again, no lab tomorrow, and probably late tomorrow afternoon, I'll be sending you the test. Okay, make sure that you write your name on all of the pages and make sure that it is legible before you send it back. Okay, so that is it. The final exam is scheduled for Wednesday, and that's going to be on Top Hat.
Are we gonna be able to like draw stuff on Top Hat?
No, it's going to be all multiple choice.
Okay.
It'll be all multiple choice.
Will we have like a time frame to do that, or will we have like all day for the final?
It'll be like all day. Okay, I know you all have different schedules. Okay, any other questions? Okay, well, that's it then. We'll go ahead and end.
Thank you.
You're welcome.